This is so typical, right? When teachers have their own answers, and if you don't get that answer, you make the students repeat. So you're forcing your thoughts on them. But at least critically analyze it.
Resolution of the camera is good, bad. Yeah.
It seems to me too. I mean, if when you go a few years back,
If you want to write through the video, then you can complete the writing. Because for the point, if you want to write with the video in the laptop, then you can write everything properly. If the word is small, then that will be blurred. I checked last 2-3 video and then I got something. For example, if you give the dot, it's if there is comma, a dot, or power, that is same.
Yeah.
Okay.
I don't know. Yeah. I think it has to do with Zoom also. The camera is okay.
The new dates are like December 21st is a solstice or something.
Yeah.
And January 3rd is a perihelion. So it's a coincidence that those two are like falling between 2 weeks.
Yeah.
In time it comes closer, but perihelion is January 3rd. December solstice.
So what is the essence of winter solstice? Geometrically speaking, what is so special about it?
That is the point at which northern hemisphere is tilted farthest away from the sun.
Yeah, December solstice marks the sun's southernmost path across our sky.
So maybe, so maybe the point is
towards the sun.
one is the center of mass, so this is the sun, right? So one you can say is that when is this a minimum, this point a minimum, and the other you can say is that when is this point a minimum.
Maybe,
Correct.
maybe that's.
But that's what you guys are to figure out.
Because even perihelion is not exactly on every year, not on January 3rd. In 2021, it's January 3rd, 2024, it's 4th.
Yeah, 2 days, there is a difference. That's because of our calendar and other thing. That's okay. That's every, or if you notice,
So,
even our.
It says like the southern hemisphere is tilted most towards the sun in December 21st. But Earth's most close to the sun is January 3rd.
Solstice is dependent on the tilt of the earth.
Yeah.
Helium is dependent on the distance.
So perihelion is the distance from the center of mass? No,
That's it.
they don't say. Okay. That might be a point, yeah. Good. Okay, that helps. So I had to make my question more precise that when is the center of the sun? The farthest or closest maybe, yeah, okay. Okay, I have to do something else. Make this big. Okay, good point. I didn't know that. Yeah, I don't know how to change. I mean, camera I think is good.
I think in 21st you like manually zoom detail time. Like the video that we are supposed to follow the homework. You manually did it throughout the lecture, I think. That's why it's more zoomed.
Oh. So it is good or bad?
It's okay. So
On 21st means which are you talking?
21st, like
Last
21st.
Oh, 2021, the one that you have to use for your lecture.
Yeah.
And that is not convenient, is it?
That's more zoomed.
So it is too zoomed in, so you don't get a bird's
No.
eye.
It's a good video.
Oh, it's good video. Okay. Is that what you would like?
Yeah.
We can do that. It's, yeah, so the way we used to do that, I thought you guys told me that you guys like it.
This one is easier, but if you zoom,
Yeah.
then those small words will be distinct.
Okay.
And there's more work to do. Yeah,
No, that's,
moving here and there.
I used to be okay with doing it. But then we always used to have students online at that time. So it was easy to,
Yeah,
I used to address
add those things, that's why you can understand that.
so. Let me try that today. Or you can set it up for several parts. Yeah, that's what I'm doing. One. I have to remember which was which. See how it goes today. Try to remind me if I'm not moving. Yeah, let's do that. So in the last week, we want to do special relativity. And I like to do it here as part of classical mechanics, because often special relativity is a topic where certain subjects say you will see it somewhere else, some others will say you will see it in math methods. The best place for it is in electromagnetism. We do it in electromagnetic course also. Maxwell's equations tell you that speed of light is a constant, immediately comes out of the consequence of that. The motivation with which it is done there is in the spirit that speed of light is a constant. Here, the way you will describe it is that not by saying that speed of light is a constant, what is the principle of relativity itself? If there is position and time, is there any other relativity you can construct, like Galilean relativity's example? Is there any other relativity there? So, and that will be the spirit in which your first homework will be. The first homework in your in the current homework that is going on will have that. And I'll try to, in the limited 2 lectures we have, cover as much as possible. And rest of it, you will have to use the lectures to do that. This will be more participation grade. I won't be testing you on this too much in detail at least. But at the same time, it doesn't mean that you can completely escape by not studying. I expect you to know Lorentz transformation, like very standard stuff which you study in, let's say, high school about special relativity. How many of you see special relativity in high school? Ryan? You do it in school, okay?
Yeah, very
Limited, yeah.
limited.
Yeah, I was afraid that you will say no. Yeah, okay, so you do see it, okay, that's good.
If you take a special physics course,
Great, so you
that's not in your typical science. course.
correct, yeah. Have you guys seen special relativity in your high school? Pradeep,
I think,
high school? 12th grade?
yeah, 12th grade, we saw a little bit like a 3 law of motion, something like that, but not.
3 laws of motion, no,
What, not
Lorentz transformation, and like length contraction, time dilation,
time dilation, yeah.
right?
We
And
go for the time dilation.
yeah, high school, that's what I mean. Nahida, yeah. No?
And time dilation, you guys do, maybe, no, relative velocity.
Late mass and time, like these three.
Relative velocity, have you seen? I like Poincare addition formula, like the velocity addition formula. Yeah, so that's good enough. Okay, so at least one. So all that involves speed of light is introduced to you, and there is some significance of that. Yeah. So what I mean is, that is at high schools, I expect those kind of things like contraction, time dilation, velocity addition. You should be aware of special relativity. If I give you a Lorentz transformation, you shouldn't come back to me and say that, oh, you never heard of it. So that's the expectations I have. But we are going to quickly at this point. So if you have very limited time, let's say you have only half an hour to study for the exam, you're spending all your time on quantum mechanics, then in that, so half an hour, you have to prioritize, you have to make some decisions. Then this is the subject you should drop. Special relativity is less probable to be asked in the final exam than other quantities. Having said that, I might ask. So I'm not saying that I won't ask, okay? Is that clear? I'm only saying if you are making a judgment as to which topic should I pick for studying, then this is a topic that might be safer. Drop. Any questions on that? Okay. Yeah, homework, and let's tell something about homework. So most of the homework done. So we have homework 12. I posted. It's due May 3rd. Friday. With buffer. Okay. Are you guys smiling? No. Something that I should know? No.
Oh, you're wondering about these final exam also?
Yes, final exam is also posted. Posted it.
Over 12 a.m.
Yeah, final exam. I just posted it. Maybe you guys checked yesterday or something. I posted it today morning. So this is May 9th. Thursday, 2:45. 4:40. Every submission, everything after May, after this Thursday, everything is late. Okay, so all delayed is okay, but try to finish it way before May 4th, preferably. In the worst case, May 4th is the deadline. Okay, after that, it's serious. Okay, so don't go beyond. But there are 5 questions in this. 1 and 2. This will be in class. 3, 4, and 5. This is take home in the sense that you have to do it and bring it to the class. So bring from home, right? Not take home. Bring from home. I don't know what's the right word for that. Right? Bring from home. So it's already available. Cheap. You can submit it early if you want. That's acceptable. Problem 3, 4, and 5, then I can grade it for you guys. But either way, I don't plan to strictly grade. It won't be too much seriously graded. I think. Yeah, we have to. That's a good idea. Good. Is there any? And you're allowed to take help for 3, 4, 5 from me, from everyone, and all those homework. This will be treated like a homework. Basically, that's a. Okay, so you're going to be tested for 2 problems. And I already told you, if you get, what is it? If you get a total of 80, that's equivalent to 90 because I'm going to curve by 50%. Whatever you lose, I'll give you 50% of your grade back. And 90 is the cutoff. Okay, and remember, even if you reach 89, that's good enough. It becomes 90 because I round off. If you get 89 point, a small real number, then I round it off to 90. So that's the idea. So it's in your code. I don't decide. Grade in a sense. Okay. Any questions you have on that? You, especially Pooja and Pradeep, because others have done this before. But you roughly, I think other exams you have taken with me, so you roughly know what it is. And don't give up. all of you have a chance for an A. So that's a bit of- Okay, so I was talking about special relativity. You probably you already saw this in this course. When we write Newton's laws of motion, it is written in terms of acceleration. Acceleration is written in terms of position and time. And often we have a variable associated with it, x and t. X is a coordinate, we say, right, along a straight line. So that's some concept that was developed only in around 15th century. Before 15th century, we didn't have this idea of a coordinate x, the whole idea of algebra, that x plus y, when we associate a function with respect to x, that was not that. Before that, it was all purely geometric, or at least in a very broad way, if you look at it, it was all geometric. You had theorems related to geometric shapes, but not algebra as such. You didn't have a coordinate available. So the point I'm trying to convey is that coordinate is a artificial concept we created for our convenience. It's extremely powerful. Right after it came, Newton's laws showed up, right, within 100 years. So obviously it helped the thought process so significantly that complicated ideas could be written down on a sheet of paper. But that also led to the idea that these are all coordinate dependent quantities. How exactly do they depend on it? And that's what we want to phrase. And as I was trying to say that if you saw Lagrangian mechanics, you will see that when we rotate the coordinates, or we generalize, when we choose the appropriate generalized coordinates, then equations become significantly easier. Even a complicated problem can be written in a simple manner. So there's a lot of coordinate picking of the right coordinate plays an important role. So that's broadly where we are. And we want to now explore very critically at the very basic structure itself. What is a coordinate? How are they related? So let's begin with, so let's call it, this is principle of relativity. Principle of change camera. Oh, yes. Beginning itself, okay. You know, principles of relativity. And the idea is going to be simple. Let's stay in one dimension. So that's your straight line, let's say, and that's a road. This line represents a straight road. Interstate 57 is relatively straight, so that represents that road. And there is someone standing on the road, on the side of the road, let's say, and that person is not moving. And there is a car that is moving forward, and that could be with some velocity. I don't want to bring that up now. And that is another car that's moving with another velocity. Let's call this A, and that's B. And that's a person is staying as it is. The position of the car A can be written as XA. We'll quickly change this to X prime and X itself. And this one could be B. And immediately we also want to say, what is this? Or let's say if this is A, and we can give this a name, that ground, because he or she is standing on the ground. This is position of A with respect to ground. This is B with respect to G. So the notation is position of A with respect to G, right? That's the notation. And this one immediately is X position of B with respect to A. That should be straightforward. And what's the connection between them? We can see this geometrically. Geometrically, we see that this plus this should be equal to this. It cannot be surprising there at all. But let me write that in the following form. So let me say, okay, so XBA. Yeah, let me write this as XBG is equal to, start from here, XBA plus XAG. Again, that should be very straightforward, nothing surprising in there. But now let's say I'm interested in the velocity of each one of these objects. So I would like to talk about at what rate is the position B with respect to G changing with time. So I'm doing calculus now. Like the moment I talk about velocity, I'm doing calculus, and Galileo would come and say, oh, that's straightforward. I will simply divide out by time, or I will take the derivative. Each one of this is a function of time, and you would say this is this, right? This is dt, that's equal to XBA over dt plus and so this is what Galileo would do. And this is velocity of B with respect to G is equal to velocity of B with respect to A plus velocity of A with respect to G. And it makes sense that velocity of B with respect to G, so let's say that's going at 70 miles. So whatever is with respect to the ground, the speedometer, what shows in your car when you're driving on the whatever shows up on the speedometer, that's with respect to the ground. The wheel are in touch with the ground, right? So that's your, let's say 70 miles per hour. A could be going at 50 miles per hour, then you would say immediately that, oh, that's 20 miles per hour. So if you're sitting in A, B seems to be slower. Like you're already going at a speed, if you're going in the same direction, they look slower. So what could be wrong in here? So that's Galilean relativity, and you, some of you or most of you said that you have some feel for special relativity. What could be wrong in this?
If you increase the speed towards the speed of light.
Yeah, let's say these are all fast. I give the example of 70 miles per hour. Let's say these are electrons. These are two electrons, and that's an observer, that's the experimentalist sitting and watching those two electrons. What's wrong in this statement? Or what did I mess up? There are 3 steps, right? There's nothing else you could have done. Time, yeah, good. And what went wrong with time?
It's there, you're just taking. You're like distributing the derivative.
Derivative.
Time.
Yeah, so
take time. Like for XB.
yeah, I think what both of you are trying to tell is that what I did here is that I divided out an equal amount of time for all 3 of them.
Yeah.
Where the assumption is that the time measured by B is the same as time, or B with respect to G, time measured for B with respect to G, B with respect to A, and A with respect to G is all the same. That means there is some universal clock sitting there, everyone can refer to it, which is like saying, which is what we exactly do in the town hall. There is a big tower we create, and there's a time, and we all look at it, and it seems like that work. In fact, even our cell phone has that same simple idea that time is the same for all of us. But that's not the same. That's the idea, or that is the proposal we make, that what if time is not the same? So this is the equation for position. But now for time, by doing this, what we have assumed is that time is the same. So delta t is same. And we can question that. And Galileo did not question that, and you immediately get the Galilean relativistic formula. And now we want to say that time is not the same, and that is what Einstein came and proposed, that it is different. And what is that transformation? That's what is called the Lorentz transformation. And I motivate this in your homework as to how do you get that transformation. We won't do that here because there are only 2 lectures, so I'll skip how you can derive the Lorentz transformation. That's part of your homework. We will do this again somewhere else in electromagnetism, so you will get more opportunities, but otherwise homework is the right place, okay? And so if time is not the same, we have to talk about how does the time relate when one is moving? So what we are saying is that if I have a watch, you have a watch, and if you're moving with respect to each other, then your time will not be the same as my time. What I measure will not match with your measurement. And that leads to serious issues as to if it doesn't match, then how do we compare? Right, so if you're measuring something in your lab, let's say time in your lab, and your friend who is in on another planet, who is moving relatively with us with respect to us, does another measurement, what do you match? Because we already agreed that time is not going to match. And how do you translate from one to the other? It's exactly like units. There is nothing wrong in measuring in different units. It's just that you should know the conversion. As far as you know the conversion, that's good enough. And that is even better. The thing is that measure things that doesn't change with respect to velocity. So we will come up with quantities called invariant quantities that does not depend on the reference frame with which you're using. So Lorentz transformation. So we come to Lorentz transformation. So you're saying that there is again a here it was possible to talk in terms of a single line because there was only x showing up, but all of you guys are in front of me. I don't have to look that. But thank you for keep everything was happening along a line, so there was only one variable involved here. But now we want to bring in time also. So let's say this is your z, and that's your time. And we use z instead of x, it doesn't matter, you can use x also, that's perfectly fine. That is another coordinate, another frame, let's say this is your car that is moving with velocity v. That's your t prime now, let's say that's your z. And we want to again talk about what's the connection between the two, and we will say this is z prime is equal to, again, this z minus vt should always be there, right? Or it didn't show up here. It should depend on velocity times time, but let's say this is equal to, I'm just going to write down the equation. So that's gamma, write down gamma times z plus beta times gamma times c times t. So treat this as a single variable. It's what are the dimensions of z, that's length, and what are the dimensions of c times time?
That'd be length.
That would be length again, right? So that's the convenience of using this. So this is length, that's length, that is length. So what is the dimension of gamma?
Dimensionless.
Dimensionless because length are alike. What is the dimension of beta and gamma together? Dimensionless again because there's already a length in here. So the notation we use is beta will be V over C. And the way Lorentz transformation works, beta should always be less than 1 and greater than or equal to 0. Actually, it can be 1 also, right? Speed of light is allowed in here. So beta can be 1, which means it is speed of light, and 0 means it is at rest. Another variable that showed up is gamma. It's equal to 1 over 1 minus beta squared. But beta is V over C. And if beta is always less than 1, gamma will always be greater than or equal to 1. When beta is equal to 0, it is equal to 1. When as you increase your beta, as you get closer and closer to 1, as you get closer and closer to the speed of light, this gets larger and larger to 1. It gets larger, that means this denominator gets smaller and it can go all the way to infinity. The largest value. So when beta is equal to 1, gamma is really large. So gamma is often called the Lorentz factor. If Lorentz factor is large, that means relativistic effects are significantly larger. And the Lorentz transformation is given as Ct prime is equal to beta times gamma C plus gamma times C times T. And this is all, if you write it as a combination, then it helps to realize. It's good to see this as a matrix transformation. Like this is perfectly fine. There is nothing new in writing it in one form or the other. That's gamma, beta, gamma, beta, gamma, and gamma. That's the same information in there. One thing we can immediately do is, if you have a matrix, we can find the determinant of that matrix, right? And the determinant of that matrix is equal to, so let me say this is gamma squared minus of beta gamma squared. What is that equal to? Very good. So that's equal to 1. Right, if you do the algebra, so if you don't plus that, so that's 1 over 1 minus beta squared minus beta squared over 1 minus beta squared. Denominator is common, numerator can be put together, that's equal to 1. That plays an important role. So this is the difference between the multiplication of the diagonal elements is equal to 1. And we want to see the geometry of this. Now we are saying that, notice, again, we want to appreciate that there is a coordinate z and t, you measure in one frame. Z prime and t prime, you measure it in another frame. The only difference is that one is moving with respect to the other. And we are asking how are they related? And they are related by this quantity and we want to get a physical insight of this. So there is something very similar we do, and that is rotations. Move my camera. Remind ourselves of rotation.
So having determinantly equal to 1 is some speciality.
Yes, I will show that in a minute. That's what I'm going to highlight at this point. What is the importance of this? It seems like this is just, especially when you look at it, this there's nothing special, right? It's just algebra. It is just an algebraic relation, but I'm going to show that no, this has a significance that that we will that's where I'm comparing it with rotation, and I'll come back to that. Okay. So let's go back to rotation. Here we have Z and T, and we have a similar concept in here, and that's X and Y. Like this is your X. And yeah, let me not write what is X and what is Y. If I have a coordinate, let's say down there, that's my X and that's my Y. Right. That's the idea of a coordinate system. Give me a point, and I use. Remember again, this is a physical quantity. This is our artifact. Like for our convenience, we keep our coordinate system. This has nothing to do with nature. We created this concept of a coordinate system. Rotate this coordinate system a little. That's what would happen if two students independently try to measure the coordinates for the same point. And they will, that person would say, oh, that's my X, which is X prime now. And this is your Y prime. Is that clear? And if this was angle theta, then they are related by X prime and Y prime are related to X and Y. In what way are they related? Very good. Cosine theta, sine theta minus sine theta, cosine theta, and X and Y. Okay. And what's the determinant in here of the matrix? Cosine square theta,
Right, equal to 1.
this time plus sine square theta is equal to 1.
Unit circle.
Unit circles. But what's unit circle about? This cosine square plus sine square theta is just a trigonometric relation. Where is the circle coming in? That's just a criticism or trying to point out. There was a question earlier as to what's the essence of this, right? Here, this seems to be just a trigonometric relation independent of a circle, but apparently this has a lot of connection with a circle, right?
Yeah.
So let's try to connect it again with that. Yes, comment?
Yeah, I was just thinking cosine theta is equal to X over this of a circle.
Yeah, so you circle, right? So immediately you come up with a circle. So let's look at this again, right? Let's look at this transformation again. This is good, very good, right? But it seems like you're giving a lot of essence to this point, and you're moving the whole coordinate system for that. Instead, let's keep the coordinate system still, and we're going to move the particle move. This is called passive rotation. Whatever I've done just now is called passive rotation in the sense that the axis has been rotated. Now let's do the same thing with what is called active rotation. And now what we have is, so we have a circle. And let me have this as my coordinate x, y. The understanding is that the moment I give my point x5, there is this coordinate. The projection of that point on that coordinate axis is my x and y. But this can also be thought of as keep the coordinate the same and move the point. What has happened here is that this point has got closer to the x-axis. So move this to this point, that's my x prime, y prime. My point is don't move the axis, instead move the point. So this is your x, y, that's your x prime, y prime. The point has moved, and that's your angle theta. Again, showing up the same way. But now, it's not very convincing that this should have moved exactly on a circle. I haven't told you that, I haven't shown you that at all. We will prove that in a minute. But if you take my word that geometrically there is a good meaning here, that okay, there is a point on a circle. When I move away on another point on the circle, that is the same point as measured by another observer who has moved the axis. Right? In this sense of saying that. So these 2 points are connected. In the sense, if you rotate it, you won't see any difference. Right? All these points on a circle are the same point, but measured by different people in different rotated frames. Right? That's the essence of that circle. How do you show that that's really a circle? Do this. So x prime square plus y prime square is equal to, that's cosine theta x plus sine theta y, the whole square, plus minus sine theta x plus cosine theta y, the whole square. That's equal to cosine square theta plus sine square theta times x square. Notice cosine square plus sine square theta showing up. The y components are again sine, so theta, right? Sine square theta plus cosine square theta, y square, and finally there are cross terms which basically cancel out to cosine theta, sine theta, xy, and minus 2 sine theta, cosine theta, x and y. The cross terms cancel out. And cosine square plus sine square theta 1, right? The essence of this point, y, the determinant matter, that's equal to x square plus y square. So whatever this transformation is doing is that it is keeping this distance constant. And you look and you ask in geometry, what is a curve which keeps this distance constant? And that's a circle, right? X square plus y square is equal to a constant if it's a positive number. So these are sum of 2 real numbers that are squared, so it must be positive, or it can be 0 if x and y is 0, so it has to be positive, and it must, so you write it as an a square, so x square plus y square is equal to a square is a constant, so that's the equation of a circle. Right? That is how you show this point goes in on a circle. But now what is the meaning of each point on the circle? They are the same observation of the same point with respect to different coordinate system. that are rotated a little bit. Like a new interpretation of the points on a circle, x prime plus y prime is a coordinate of the same coordinate xy, but this time rotated off. It's measured by a object that is slightly rotated. Good. So, can we do something here? What is the geometry associated with Lorentz transformation? Okay, so let's go back. We will, instead of looking at this is more intricate. We have to talk about the axis. What kind of axis are we moving? Instead, we can do this algebra very quickly. Right? Let's do this algebra and see what comes out to be a constant. Which equation is kept the same by Lorentz transformation? So let's do that. For Lorentz transformation, we find so I'm going to go in the reverse order. So in rotations, I gave you the answer first. Instead, in Lorentz transformation, first let's do this algebra, see what is constant, and then we'll plot that and see what that curve is. So let's look for z prime. And why this particular combination? Again, because of the relation between the two, right? It seems like it is plus here. It was minus that was remaining the same. So probably it's going to be minus that. So that's a guess I'm making. So that's equal to z prime is gamma z plus beta gamma ct. So, and minus of beta gamma z and plus gamma times c times t squared. Again, do the algebra. Readable. So it's equal to collect the z square terms. So it is gamma square minus beta square gamma square. And you see that combination coming again, right? And next, let me write it as a minus sign of it's minus sign, so I have to write gamma first. So gamma square minus beta square gamma square c square t square. And the cross terms, it is convincing that the cross term will be the same, correct? Both are positive and there is a minus sign in between, so cross terms has to go. And again, this is equal to 1, right? Essence of why this was an algebraic statement, but that plays a very important role in recognizing the coefficient to be equal to 1. So that's also equal to 1. So that's z square minus c square t square. So again, go back to our interpretation. If you have a curve which keeps something constant on that curve, each point is the same information measured by different coordinate system. In this case, it was rotation measured by angle theta. In this case, it is beta measured by the relative velocity. Right. So what is that? So our equation saying that z square minus c square t square is a constant, right? Let's call it a square. A square. But there is a problem here. There's one small difference. In a circle, this was the sum of two positive numbers. So this had to be positive. But now a square doesn't have to be positive. Right? So a square can be 0, for example. That's allowed. A square is, so even saying a square is misleading in the sense square quantity is always positive, so let's not give it a name, right? So question mark itself, I don't want to write it as a square quantity is never less than 0, right? So it will be misleading. So this could be less than 0 and this could be greater than 0. Right? All three is possible because the square accordingly will be different. What is the curve for this? When this is fixed, what curve represents? Well, my question is x squared plus y squared is equal to a squared. Let's say something positive, right? That's a circle. What's the equation of this? Like what curve is given by that formula? Hyperbola, right? So that's a hyperbola. And so we say that. So that's my c times t, and that's my z. Okay. Notice in most of the introductory physics courses that probably you guys teach, and almost universally, almost all textbooks will have that as position, this is time. Right? This is the opposite. So what will be the slope of a curve in this? Slope of a curve in ZT curve is velocity. In this case, it is the inverse of the velocity. Okay, so don't confuse, it can lead to simple careless mistakes in your interpretation. Okay, if you were to plot this, notice x square minus y square is a constant. Let us say that it is positive, correct? So z square is if it was positive, let's say if this was, let's first say that this is fixed, right? I didn't even put a number there. And now let's say z square minus c square t square is greater than 0. That means z is greater than ct. The z here is larger than length. So if I have a point that differentiates this into 2, all points that are on the right side of this line, which is making a 45 degrees, is z square is greater than ct. And that's the primarily because I scaled it off with c. So this point is an example. This is greater than t, and the equation of this hyperbola is like this. So this is, for example, z comma ct, exactly in the spirit of passive transformation. That's z comma ct. I can remove this z and t. So now this is z comma c. If I were to make the same observation with respect to another frame, which is moving with a velocity v, so I have changed my beta, that will be somewhere here or there. I can move it around. That's z prime, c t prime. Is that clear? Each point in on this curve will be, so this is c double t prime, another point, another coordinate system measuring the same point, which is actually moving with respect to the this was all for points where z is greater than t. If z is less than t, that comes in here. And again, you can go around on those points. You can also have, since this is a squared quantity, you can have plus or minus and then get the same thing. So you have this also given by the same idea. And that leaves us with the straight lines. What if it was exactly equal to 0? Right? Those are the straight lines. So that's, so, so that's a straight line. I think I hope I don't want to say it. But what is interesting is that still the slope will represent, if this was the curve or maybe a caution, right? These lines or these curves, right? Do not represent a path of a particle. And why is that? First of all, because the way we interpret it, like this is just a transformation, right? The transformation was connecting them. But what do I mean by that? Let us say that, hypothetically speaking, a particle actually goes along this line. Okay. Which would mean that, what is its velocity right at this point? What's the slope of that point? Slope is 0. So for this point, let's say point A. So point A on that curve, slope is equal to 0. Slope is, remember, this was position and that was time, right? Slope is not velocity, it is inverse of the velocity, right? So that means velocity would be 1 over 0, right? Which is infinity, right? So a particle cannot go at that speed in our way of saying. So this is not allowed. This curve is not possible. In fact, what is the speed at this point? Is it greater than speed of light or less than speed of light?
Getting near its speed, right?
Yeah, but at this point, let's say B, and A prime, let's say, is it greater than speed of light or less than speed of light? The 45-degree angle is speed of light, right? If I go this way, remember,
Greater.
yeah, it's greater because slope, remember, is opposite. If I get this, it is 0, so that's a confusion, or we are so much tuned for z being on the y-axis. So be careful with reading this off. Right? So all physical orbits are most probably of this kind, like the actual particles that move. These regions in this Lorentz space are called or these events, I should say, whenever this is greater, these are called space-like events. Whenever it is less than 0, it's called time-like. And if it is equal to 0, that's called light-like. Okay.
When we take the slope of the graph,
Mhm.
CT is having the units of distance. C is having the units of distance.
Oh, it measures beta. Okay. Beta, 1 over beta. Because we are in dimensionless quantities. Good, very good point that, oh, dimensionally we are off. So what are we measuring? We are measuring beta. Okay. We'll come to that in a few minutes. Okay. Okay. So let's, if this is not representing the path of a particle, what is the path of a particle, right? That's what comes to mind. So now that I've given you this connection, I can erase this probably. I'll address probably your question in a minute. So, so trajectories of particles. So let's now say this is really our coordinate that we like. This is my coordinate. I am having an z-axis and I have a clock, right? That's what this means. This is my coordinate. So each of you will have a coordinate for yourself. I am sitting right at the origin. That's me sitting there and in my own frame, I will always be at rest. So what is my position as time evolves? Now time is my watch, right? Time t equal to 1, t equal to 2, t equal to 3. In my own frame, I am at the origin. I'm not moving. It's very hard for me to move with respect to myself, right? So I'm here at time t equal to, so z is equal to 0, right? I'm here. At t equal to 1, I'm still here. Keep moving, right? So I'm moving straight. Correct? In the ZT curve, you would have said this is the horizontal line. So this is the vertical line. So this is the trajectory of someone at rest. Right? Notice the slope again. It is coming out to be infinity if you want, but that's 1 over 0. But let us say right next to me is the stool, right? Is the stool sitting, that is sitting there. That's a distance let's say 1 feet away from me. That is also at rest. Let's say that it stays 1 feet away from me all the time. That is also moving, right? With respect to 1 second, that's still there. 2 seconds, it's still there, right? Moving in the sense of on the space. So this is the stool. Stays here at this point, stays here, stays here, stays here, right? So that's another object at rest. So that's me at rest. It doesn't have to be me at 0. So that's rest. Okay. Now I want to talk about motion, right? Now let's say that stool cannot move. Let's take Manuka or Pradeep, one of you guys. So I have to sit here so that you move to the right? So you stand up and you don't like the class and you just walk out, right? So walking out, notice you get farther, right? You're 1 feet, 2 feet, 3 feet, and let's say that you go uniformly, right? 1 feet, 2 feet. So uniformly, you're going to get farther and farther, right? At t equal to 0, so that's the third person. It was he or she was here, then got farther, so farther from me and the stool, right? So that could be me and one of them is stool, and is that clear? So that's something gets farther and farther. If you had, let's take another object moving further faster, lot faster, then you would say that will be like this, right? But there's a limit to which you can go, right? This is, like, remember, that's speed of light, right? That's beta equal to 1, right? Or yeah, I said it's rest. So this is beta equal to 0. That's beta equal to, let's say, 0.1. And as you increase beta, that slope increases. When you're studying kinematics, first thing which is trivial is you're at rest, right? That's at rest. Then you talk about uniform velocity, right? Where the equations are z equal to v times t. Right? There is a z naught also that depends on the origin. That's uniform velocity. The way we are writing it, I think this will answer your question. This will be v over c times ct. So that's beta times CT. So the slope is beta. I think that might clarify your answer. But now we are still working with this equation. First, we do at rest, simplest motion. Everything is at rest. The second is that it's moving uniformly with a uniform velocity. That's this equation. The next equation we talk about is uniform acceleration. And if we are in normal life, let's say not doing relativistic physics, we are doing, if you throw a stone up in the air, what is the equation with respect to time of a stone? The trajectory of the stone, what's the equation? What's the curve that it takes?
Up in the air, so form a parabolic.
Parabola, right? So it is,
Hyperbolic.
no, parabola. Parabola, right? Z is
I
equal
was kind of thinking maybe Canterbury.
no, Z equal to, like you would say this is equal to Z. Is, let's say, start from rest. It is half AT square, right? That's the equation you get for a trajectory. It's in, this is in time, notice, that's one thing, but you can always, when you're throwing the ball, use the X distance as the time, because that grows linearly. Anything that grows monotonically can be used as time. And you can replace that, so it is parabolic, even though horizontal motion that you have. So that is a VT here, V0T, which if we start from rest, that can be killed. So parabola is an equation of uniform acceleration. Notice we have used new concepts, uniform acceleration. Uniform means constant in time. Right? Acceleration remains constant in time. What would that mean in relativity? Acceleration remains constant in time. Time is not unique at this point. Different people measure different times. So uniform acceleration, at least in this way I have told you, that acceleration remains constant in time. That's not well defined yet. I haven't told you what that means. There is no such thing as in whose time. The immediately you're asked, the moment I say that in time, in whose time are we talking about? Right? So uniform acceleration, at least in the simplistic way we say, that it's constant in time, is an issue at this point. Right? We will talk about what is called proper acceleration in the next lecture and define something called proper acceleration. So uniform acceleration, uniform acceleration is, so the word uniform is questionable, right? We don't know. In relativity is not immediately well defined. I haven't told you what this is, but instead what we will define is what is called a proper acceleration. Already we have length is not very well defined, right? Length changes from person to person. Time changes from person to person. Uniform acceleration changes from person to person. Right? So it's sort of useless. But then we will bring something which does not depend on person to person. That will be what is proper. So we want to talk about things that is not dependent on frames. We will talk about proper length, proper time, proper acceleration. Quantities that does not depend on the frame. But having said that, how will that look like? Like, it is good to know how will it look like, proper acceleration. I'm telling you that there is one frame which does not depend, which one curve that does not depend on which frame you're in. Right? Can you guess which curve does not depend on where you are? Hyperbola. Right? Hyperbola doesn't depend on which frame it is. If you pick this, it is the same, right? Z square minus C square T square. So I measure Z and T, it's a constant. Someone else measures Z prime and C prime, it's a constant. So hyperbola is an immediate solution, and this curve, so this curve here, is proper acceleration. But then you say that, oh, what about the slope? Is this going faster than light or slower than light? Yeah. Slower, very good, right? It's slower because the slope is all less than this, right? It never reaches that. So it is slower, so it is good, even though it can be misleading because I drew it on this side, right? That has nothing to do with it. Has the slope that matters. Particles can be on this side of on the space-like region. That has nothing to do with it. It's a slope that matters. If a particle is going, you have to talk about the slope. Slope can never be faster than speed of light. It doesn't mean that on this part or on that part it cannot. Here, this goes faster than speed of light. Here also it goes faster than speed of light. Here also this goes faster than speed of light. This is okay. That's perfectly fine. Doesn't matter this one. Right? All these vertical lines are all going slow, and horizontal lines are just not possible. So now we have to bring up the idea of proper acceleration, and that is what the most of what we will do next lecture is. We will talk about, first of all, we have to define velocity. Even velocity is a problem, right? What do we mean by uniform velocity? If I'm moving uniformly with respect to you, I may not be moving. If you move around, it is not. So even uniform velocity, how much is that uniform velocity is an issue. Right, so we will define something called or we'll define a proper time. That's what we will do, and then so we'll change the calculus. So, okay, that's all. Thank you.